In this lecture, we will talk about oxidation numbers, redox reactions, and balancing simple redox reactions. Oxidation-reduction reactions are processes in which one or more electrons are transferred between reactants. The number of electrons assigned to individual atoms in the various reactants change. All reactions involving covalent compounds are classified as redox reactions because electrons are rearranged as bonds are broken and new bonds are formed. To keep track of changes in electron sharing and to determine if atoms are oxidized or reduced in redox reaction, we use oxidation numbers. Oxidation number or oxidation state indicates whether the atom is neutral, electron rich, or electron poor. By comparing the oxidation number of an atom before and after reaction, we can tell if it gained or lost electrons. Oxidation numbers do not necessarily imply ionic charges. Historically, oxidation referred to the combination of an element with oxygen to yield an oxide, and reduction meant removal of oxygen from an oxide to yield the element. Now we use wider terms for oxidation and reduction. Oxidation means the loss of one or more electrons by an atom, and reduction means gain of one or more electrons. The redox reactions are characterized by electron transfer between species or a change in oxidation number of atoms. For example, calcium metal or elemental calcium reacts with elemental oxygen, producing calcium oxide. This is a good example of a redox reaction. Let's assign charges for all elements and ions in this reaction to keep track of electrons. We already know that elements are neutral because they have the same number of electrons and protons. So we can assign charge 0 for calcium and oxygen. Calcium oxide is an ionic compound, and we are familiar with the ions. We can assign charges to these ions. We know that since calcium in the second group in the periodic table, it tends to lose 2 electrons and form positively charged calcium 2+ ion. So the charge of calcium is +2. We can represent this as calcium element loses 2 electrons and forms positively charged cation. Oxygen is nonmetal. We know that nonmetals tend to gain electrons. Oxygen gains 2 electrons and becomes negatively charged anion. The loss of electrons means oxidation, so in this example, calcium is oxidized. Gain of electrons means reduction, so oxygen is reduced. Now let's talk about oxidation numbers and how to assign oxidation numbers to all atoms present in a given molecule or ionic compound. Rule number 1. The oxidation number of an atom in an element is 0. In other words, all elements are neutral and the oxidation state of any element, whether it's a polyatomic element or diatomic element or monatomic element, the oxidation state of an element is 0. For example, the oxidation state of oxygen, O2, is 0. Oxidation state of phosphorus, polyatomic element P4, is 0. Oxidation state of sulfur, polyatomic element S8, is 0. Sodium metal, 0, and so on. Ozone is a molecule. It consists of 3 oxygen atoms, but it can be considered an elemental state as well. All of the atoms are the same, so molecules like this would have oxidation state 0 as well. Rule number 2. The oxidation number of an atom in a monatomic ion equals the charge on the ion. For example, fluoride ion, F-, has the oxidation state the same as the charge, -1. Aluminum 3+. Oxidation state of aluminum is +3, same as the charge of an ion. Rule number 3. The oxidation number of oxygen is usually -2 in most of its compound. There is one exception to this rule. In peroxides like hydrogen peroxide, H2O2, the oxidation state of oxygen is -1. This is the only one exception. In all other compounds like water, H2O, oxidation state of oxygen is -2. Any oxide, barium oxide, for example, oxidation state of oxygen is -2. any molecular compound, sugar, the oxidation state of oxygen is still -2. Methanol, oxygen has -2 oxidation state. Rule number 4. The oxidation number of hydrogen is usually +1 in most of its compounds. The only exception for hydrogen is when it is in the binary compounds with a metal, forming metal hydrides, like calcium hydride. In hydrides, in combination with metals, the oxidation state of hydrogen is -1. In all other compounds, like water, methanol, the oxidation state of hydrogen is +1. Rule number 5, halogens. The oxidation number of fluorine is always -1 in all of its compounds. Each of the other halogens, chlorine, bromine, iodine, has an oxidation number of -1 in binary compounds, except when the other element is another halogen above it in the periodic table, or the other element is oxygen. For example, in carbon tetrafluoride, CF4, the oxidation state of fluorine is -1. In sodium fluoride, it's -1 as well. For other halogens, they usually have the -1 oxidation state. For example, carbon tetrachloride, the oxidation state of each chlorine atom is -4. The exception is the binary compound with another halogen, like ICl3, for example, iodine trichloride. In this case, chlorine would have -1 oxidation state, but iodine would have +3 oxidation state. Rule number 6. The sum of the oxidation numbers of the atoms in a compound is 0. The sum of the oxidation numbers of the atoms in a polyatomic ion equals the charge on the ion. For example, in nitrate NO3-, the oxidation state of the polyatomic ion is equal to the -1, equals to the charge of the ion. If I want to assign individual oxidation state for oxygen and nitrogen, I will start with the oxygen, since I know that oxygen has -2 oxidation state in most of its compounds or ions, and then assign appropriate oxidation state for the nitrogen to have the overall oxidation state -1. So in this case, a nitrogen would have +5 oxidation state. +5 minus 2 times 3 for oxygen, since we have 3 atoms of oxygen here, gives me -1 oxidation state for the whole ion. For molecular compounds like iodine trichloride, the overall oxidation state is 0. Each chlorine has -1 oxidation state. There are 3 chlorines here, therefore the iodine has +3 oxidation state to make the overall sum 0. Same applies to the carbon tetrachloride. Since each chlorine has oxidation state -1, there are 4 chlorines in this molecule, then the oxidation state of carbon is +4. So +4 minus 4 gives me 0 oxidation state for the molecule. Now let's practice assigning oxidation states for all the atoms in given molecules or ions. First example is MnO2, manganese 4 oxide. For ionic compounds, it's quite easy. We know that oxidation states are the same as the charges of the ions. So for oxide, the oxidation state is -2. Since there are 2 oxygen, each of this oxygen will have -2 oxidation state. Means that manganese has +4 oxidation state. So +4 minus 2 times 2 gives me neutral formula unit for manganese 4 oxide. For manganate ion, MnO4-, we know that the oxidation state of the whole ion will be equal to the -1. We can start with oxygen, since oxygen always has -2 oxidation state. Now we have 4 oxygens here, so that's going to be -8 for all of the oxygens, which means that the manganese has +7 oxidation state. +7 minus 2 times 4 will give me -1. Ammonium cation, NH4+, +1 for each hydrogen. The oxidation state of the whole cation is +1. There are 4 hydrogens, so +1 times 4, which means that nitrogen has -3 oxidation state. -3 plus 4 gives me +1 for the whole ion. Sodium dichromate. First of all, we can break this ionic compound into ions. We know that sodium cation has +1 charge, so the oxidation of sodium, each sodium cation, will be +1. Dichromate has the oxidation state -2. This is overall oxidation state for the whole ion. Now we can assign the oxidation state for oxygen. Each oxygen has -2 oxidation state, so -2 times 7, that's gonna give us -14. And this is a neutral compound, so we need to have +14. We already have +2 sodium cations. Let's say +1 times 2. Means that chromium will have positive oxidation state, and there are 2 chromium atoms here. So if I subtract 2 from the 14, -14 plus 2, it equals 12. And then I'm going to divide this 12 by 2 for each chromium atom, since all of the chromium atoms will have the same oxidation number. So it's going to give me +6 for each chromium. +6 times 2. So 2 plus 12 is 14, minus 14 gives us 0 for neutral ionic formula unit. Sodium chromate. Each sodium cation has oxidation state +1. Oxygen has oxidation state -2, so that's going to give me -8 for oxygen, +2 for 2 sodium cations. To have an overall 0 oxidation state, I will need +6 for chromium. So +2 plus 6 minus 8 is 0. Perchlorate anion has negative charge, so oxidation state of the whole ion, polyatomic ion, is -1. We can start with oxygen as always. -2 for oxygen. That's going to give us -8 for 4 oxygens, which means that chlorine has +7 oxidation state. So as you can see in this example, we have one of the exceptions for the halogens. In polyatomic ions, in combination of oxygens, halogens may have various oxidation numbers, not necessarily -1. So +7 minus 8 is equal to -1. P4 is an elemental phosphorus, and oxidation state of elements is 0. And then P2O7 diphosphorus heptoxide. Start with the oxygen, -2 times 7, that's -14 for 7 oxygen atoms. This is neutral compound. So for the phosphorus, we would need +7 oxidation state. +7 times 2 is 14, minus 14 equals 0. Ethanol, C2H5OH. In molecular compounds like this, always start with hydrogens and oxygens. Hydrogens have oxidation state +1. Oxygen has oxidation state -2. So let's see what we have. We have 6 hydrogens. That's going to be +6 minus 2. This is neutral molecule. And we have 2 carbons in this molecule. The oxidation state of each carbon is going to be -2. So -2 times 2, that's going to be -4, plus 6 minus 2 is equal to 0. Next, C6H12O6. Let's start with oxygens, -2. Each hydrogen has +1 oxidation state. So +12 for all the hydrogens, -12 for all oxygens. Overall neutral compound. It means that the carbon has oxidation state 0. 0 times 6 plus 12 minus 12 equals to 0. Carbon dioxide, CO2. Oxygen has -2 oxidation state, so -4 for all the oxygens, and it means we need +4 for the carbon. C5H12 +1 oxidation state for hydrogen, +12 for all the hydrogens. Now this compound is organic compound, molecular compound, and it's a little bit more complicated. In this example, we would need to look at individual carbon atoms. So let's draw the structure of the C5H12. Each carbon makes 4 bonds, 4 single bonds with hydrogens. We can also represent this with condensed formula, CH3, CH2, 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 CH3. So we know that each hydrogen will have +1 oxidation state without exceptions. Now if we look at the individual fragments in this molecule, we have CH3 groups that are called methyl groups, and CH2 groups are called methylene groups. So in each methylene, in each CH2, we have 2 hydrogen atoms. Each of the hydrogens has +1 oxidation state, so +2 for hydrogens overall. And we can assign the -2 oxidation state for carbon, -2 + 2. This would give us the 0 oxidation state for each link, each methylene link in this molecule. So all of the carbons in methylenes will have the same oxidation state, -2, -2. However, in methyl groups, in CH3 groups, we have 3 hydrogens attached to each carbon, and each hydrogen has +1 oxidation state. So the oxidation state of carbons in this group is going to be -3. -3 + 3 for all the hydrogens. -3 for carbon in methylene group. So the sum of all the oxidation state for all carbon atoms in this molecule is -12. But you can see that oxidation state for different carbons vary in this case, because some of them will have -2 oxidation states, some of them will have -3 oxidation states. Essentially, it depends on how many hydrogens are attached to this particular carbon. What is the oxidation state of nitrogen in the compound dinitrogen pentoxide in 2O5? Start with the oxygen, -2 times 5, that's going to be -10. This is neutral compound, neutral molecule, so we need +10 for nitrogen, and there are 2 nitrogens here, which means that each nitrogen will have +5 oxidation state. +5 times 2 minus 10 gives us 0. Correct answer is D. If nitrate NO3- is converted to dinitrogen pentoxide, the nitrogen is oxidized, reduced, neither oxidized or reduced. Remember what is oxidation, what is reduction. We can use simple abbreviation, OLRIG. Oxidation is loss of an electron or electrons, and reduction is gain. When something gains electrons, it becomes less positive or more negative. To figure out whether nitrogen is losing or gaining electrons, we need to track the oxidation states. Let's assign the oxidation states for all atoms. In nitrate, this is negatively charged anion. Oxygen has oxidation state -2, so that's -6 for 3 oxygens. Overall oxidation state is -1, which means that nitrogen needs oxidation state +5. +5 minus 6 equals -1. Now let's look at N2O5. -2 for oxygen. This is neutral molecule. Sum of all oxidation states is 0. And looks like nitrogen has +5 oxidation state as well. So +5 times 2 minus 10 equals 0. This means that nitrogen is not losing or gaining electrons. It keeps its oxidation number the same. So nothing happens to the nitrogen in this case. It's neither oxidized or reduced. There are many examples of the redox reactions. For example, corrosion, it's deterioration of the metal by oxidation. Combustion, burning of fuel by rapid oxidation with oxygen and air. Respiration, the process of breathing and using oxygen for many biological redox reactions. Bleaching is used to decolorize colored materials. Redox reactions are also used in metallurgy, the extracting and purifying metals from their ores. All of these reactions can be classified as, first classification is combination reaction. 2 elements combine and form a binary compound. For each of these examples, let's assign oxidation states for all the atoms involved in the reaction, and let's figure out what is oxidized and what is reduced in this reaction. Elemental antimony reacts with elemental chlorine, and we know that all the elements have neutral 0 oxidation states. Antimony trichloride, the chlorine has -1 oxidation state. This is for each chlorine, means that the antimony will have +3 oxidation state. Now let's look at what is oxidized and what is reduced. Oxidation is loss of electrons and reduction is gain. Antimony becomes more positive, it means it loses electrons and is oxidized. Chlorine becomes more negative, it means it gains electrons and is reduced. Since antimony is oxidized, it causes the reduction of chlorine. So antimony itself is acting as reducing agent. So the substance that's being oxidized causes the reduction, acts as reducing agent. The substance that is reduced causes the oxidation and acts as oxidizing agent. Note that to keep track of the electron movement, electron transfer in this reaction, we assign the oxidation states for all of the atoms in the products and in the reactants. But oxidation and reduction happens to reactants only. We cannot say that antimony trichloride was oxidized or reduced. It just doesn't make sense. This happened after the reaction. This is a product. The redox, the oxidation or reduction process happened to the reactants. So antimony is oxidized, chlorine is reduced. Second type of redox reactions is called decomposition. For example, potassium chlorate decomposes to potassium chloride and oxygen. Decomposition often involves heating. So let's assign oxidation states for all the atoms in this example. Oxygen is -2, has -2 oxidation state. Now, potassium chlorate is an ionic compound. We can break it down into ions, K plus, ClO3 minus. Since potassium has +1 charge, the oxidation state of potassium is +1. And now let's figure out the charge of chlorine here. We have +1 for potassium, -6 for all the oxygens, and chlorine would have +5 oxidation state. So +6 minus 6 equals 0. Potassium chloride. This is simple, it's ionic compound. Chloride has -1 charge, -1 oxidation state. Potassium has +1 oxidation state. Elemental oxygen. Pay attention to the states as well. So the atomic element oxygen gas has 0 oxidation state, neutral. So redox will happen to potassium chlorate. It will happen for the atoms in potassium chlorate. It's not going to happen on the product side. So let's see what's changing the oxidation state. Potassium stays the same. Chlorine changes the oxidation state and oxygen changes the oxidation state. Oxygen becomes less negative. It means it loses electrons. It goes from -2 to 0. It loses 2 electrons. So oxygen loses electrons and is oxidized. Chlorine gains electrons, becomes more negative, goes from +5 to -1 oxidation state. Gains and is reduced. We can also say that chlorine, since it's reduced, it causes the oxidation, so it's our oxidizing agent. And oxygen is reducing agent. It causes the reduction of chlorine. Next type of redox reaction is combustion. Combustion is burning of fuel by rapid oxidation with oxygen. For example, combustion of pentane hydrocarbon, C5H12. Let's assign all the oxidation states, +1 for hydrogen. The carbons that have 3 hydrogens on them will have -3 oxidation state. The carbons with 2 hydrogens will have -2 oxidation states. I'm just going to say for carbons, that's going to be -12. For all the hydrogens, we'll have +12. Now, oxygen. This is the atomic element. Oxidation state is 0. Carbon dioxide. We have -2 oxidation state for oxygen, +4 for carbon. And in water, -2 for oxygen, +1 for hydrogen. In cases like this, molecular compounds can be analyzed in terms of gaining or losing oxygen. We can say that the hydrocarbon is oxidized, C5H12 overall is oxidized. So carbons will change the oxidation state. Some of them will change from -2 to +4. Some of them will change oxidation states from -3 to +4. So carbons are actually oxidized, but we can say that the overall compound is oxidized. And oxygen, since it gains electrons, it becomes more negative, goes from 0 to -2, gains electrons, and is reduced. Oxygen obviously is oxidizing agent. This is what causing the oxidation. and C5H12 is reducing agent. And the last type of redox reactions is displacement reactions. Displacement reaction is a chemical reaction in which one element replaces another element in a compound. For example, magnesium replaces hydrogen in nitric acid, forming magnesium nitrate. Let's assign the oxidation states for all the atoms. Magnesium solid, it's important to look at the states because they tell us whether the atom is an element in elemental form or not. Magnesium solid means this is magnesium metal with 0 oxidation state, elemental state. Nitric acid, start with oxygen, -2, +1 for hydrogen, +5 for nitrogen. So +6, -6, 0. Now, magnesium nitrate, this is ionic compound. We know that magnesium forms cation with 2+ charge, so the oxidation state is +2. For the nitrate, -2 for oxygen and +5 for nitrogen. Let's check the sum of all the oxidation states. +2 for magnesium. Nitrogen, since we have 2 here, it's going to multiply all the oxidation states by 2. So +5 times 2, and then -2 times 3, and times 2. This will give us 12 minus 12 equals 0. And the hydrogen gas, H2 is the atomic element, gaseous form, elemental form, oxidation state is 0. Let's see what changes the oxidation states. Looks like magnesium. It's metal. Metals tend to lose electrons and tend to be oxidized in reactions with nonmetals. So magnesium loses electrons, is oxidized. Hydrogen changes oxidation state from +1 to 0. So it gains electrons. I'm going to point to H here and is reduced. Magnesium is the reducing agent. It causes the reduction of H+, and H+ is the oxidizing agent, since it causes the oxidation of magnesium. Now let's talk a little bit about the redox behavior of elements. In general, we know that metals on the left of the periodic table tend to lose electrons and tend to form positively charged cations, and nonmetals on the right of the periodic table tend to gain electrons and form negatively charged anions. The alkali metals and alkaline earth metals on the left side of the periodic table are the most powerful reducing agents because they lose electrons so easily and they are easily oxidized. So they are electron donors, lose electrons. They're so powerful that they react with pure water. Metals in the middle, like iron or chromium, do not lose electrons that readily. They still form the cations, positively charged cations, but they are a little bit more resistant to the oxidation. So they react only with aqueous acids, but not with water. Metals near the bottom of the periodic table, bottom right of the periodic table, such as platinum, gold, react with neither acids nor water. Sometimes these metals are called noble metals. They are resistant to corrosion and oxidation. Sometimes they're called precious metals. For example, gold will react with the mixture of acids, but not with any pure acid. Let's take a look at table 4.6, an activity series for metals in aqueous solution. Even though all metals tend to lose electrons, sometimes one metal can act as the reducing agent and oxidize another metal. Metals at the top are better reducing agents, better oxidized. All of these metals, lithium, potassium, barium, calcium, better oxidized than metals at the bottom. Metal ions at the bottom of the table are better oxidizing agents, tend to be reduced, than metal ions at the top. So let's say here metals at the top are better oxidized, lose electrons easily, essentially what this means, and therefore they are better reducing agents. They cause the reduction of other elements. Metals at the bottom, actually metal ions, which are at the bottom of the table, better oxidizing agents. I'm going to say metal ions, better oxidizing agents. tend to be reduced. It's important to note that these are metal ions that tend to be reduced, not just metals, because metals form positively charged cations. So when we talk about reduction, the gain of electrons, we really talk about metal ions. So metal ions gain electrons, get reduced to neutral elemental metals. Any metal below hydrogen will not react with the H plus cation and is resistant to strong acids. So here's the hydrogen in the table. So any of these metals below hydrogen will not react with just the H plus. They will react with mixtures of acids, mixtures of strong acids, but not with just one acid. Now let's take a look at balance and simple redox reactions. Elemental aluminum reacts with silver cation and forms aluminum cation and solid silver, or elemental silver. This is a net ionic equation. It does not include spectator ions. It shows only the ions involved in the redox process and the elements involved. So first of all, we want to write separate reduction, oxidation, half reactions. I'm going to say first step, write half reactions. Let's write the half reaction for aluminum. To show that this is an element, I'm going to say solid aluminum. And then on the product side, I have aluminum cation. Aluminum becomes more positive. It means it loses electrons. So aluminum goes to the aluminum 3+. This is for the oxidation. For the reduction, we have silver plus in solution, something like silver nitrate. And silver is reduced to the elemental solid silver element with the oxidation state 0. So these are my half reactions. Now I need to balance all the atoms in these reactions. So balance the number of particles or balance in terms of mass. I'm going to say balance number of particles. This is step 2. So in our case, the number of particles is balanced. I have one aluminum on the left, one aluminum on the right. One silver on the left, one silver on the right. I don't need to do anything else in this step. Step 3, balance charge by adding electrons to the appropriate side. Balance charge. So now I'm going to take my half reactions, first oxidation, and I'm going to add electrons on each appropriate side. Since aluminum lost electrons, I'm going to show them on the right. So aluminum cation plus 3 electrons. For the reduction, silver plus gains electrons. So I'm going to say 1 electron plus silver plus. So I'm going to add my electron on the left since silver plus gains electrons. And I have elemental silver on the right. So now if we look at the charges, on the left I have aluminum with the oxidation state 0. On the right I have plus 3 and 3 electrons minus 3. So 0. For the reduction I have plus 1 for silver and negative 1 electron. So plus 1 minus 1 and 0 on the right. The charges are balanced in terms of the plus minus charges. The next step is to multiply half reactions by appropriate whole number to balance electrons. As you can see, for the aluminum we have 3 electrons and silver gains only 1 electron, so we need to balance these electrons. Balance electrons, multiply by whole number. My oxidation reaction stays the same. I don't need to do anything else, but I need to balance the number of electrons that's going to be gained by silver. And for the reduction, I'm going to multiply this half reaction by 3. This balances the electrons and all the atoms involved in half reaction. So now for the reduction, I have 3 electrons plus 3 silver cations, and on the product side, I have 3 elemental silver atoms. Now in the last step, we need to add half reactions together to generate redox reaction. So now let's see what I have. I'm going to rewrite my oxidation reaction. Solid aluminum becomes positively charged cation and loses 3 electrons. This is oxidation, and for the reduction, I have 3 electrons plus 3 silver cations, and on the product side I have 3 atoms, silver atoms. Now I can cancel the electrons on the left and on the right side of the reaction arrow and rewrite the whole equation, and it's already going to be balanced equation. Aluminum plus 3 silver cations. Product is aluminum cation plus 3 silver atoms. So now we can add appropriate coefficients. 3 in front of silver plus and 3 in front of solid elemental silver. And now this reaction is balanced.